So the next speaker is Dr. Robert Haschke. So Robert Haschke is currently the head of robotic groups within the neuroinformatic groups at Belfield University, striving to enrich the dexterous manipulation skills for our two bi-manual robot setups through interactive learning. His fields of research include neural networks, cognitive bi-manual robotics, grasping and manipulation with multi-finger dexterous hand, tactile sensing, and software integration. So today, he's going to give a talk on tactile sensors and tactile processing of human data acquisition and robot grasping.
Yeah, thanks for inviting me to this interesting workshop. I'm from Bielefeld University, from SciTech, and we are striving to understand cognition and building technology which serves the human. This includes, of course, manipulation, but all kinds of other stuff as well. Attention, learning how humans learn, and emotions, and also insect-like walking, if you like. However, our group is focusing on manipulation, so we try to understand human manipulation, grasping, and to replicate that in humans, in robots. And we do so by, first of all, recording human action, human interaction episodes, recording the hand postures as well as the interaction forces. And then we try to design appropriate controllers which kind of mimic the behavior we observe in humans for our robots. And this, of course, requires a lot of tactile sensors, not only for the robots, but also in order to sense human interaction forces in a kind of natural way when humans interact. So that's a short outline of my talk. I will introduce our zoo of tactile sensors and then give some applications of how we use them so far. Finally, reaching at threat detection and tactile surveying. So let's start with the robot tactile sensors. We started out quite early to develop those sensors, starting with a flat version, 16 by 16 array of sensors, which can be put together for having larger surfaces of tactile sensing. And our focus in developing this particular sensor was to have a really high frame rate. So at these days, the best what one could get was kind of 100 frames per second. And this one can go up to 2 kilohertz, and we will say later why we do need that high frequencies. Of course, then we wanted to integrate these tactile sensors also in our robot hands, and the big flat sensor doesn't serve that goal. So we try to miniaturize the sensors and putting them into a 3D shape, so they nicely now fit into the fingertips of our sensors. So Matej mentioned that point that we want to cover curved surfaces as well, and that's our solution to that. So we go for a 3D shaped electrode manufactured in an MID process, and all the precision electronics is nicely integrated so that it nicely integrates with our shadow robot hands. And not finishing at that point, we also wanted to cover the rest of the hand with tactile sensors as well. But there's no room at all to fit any kind of electrode or electronics there. So we went for a completely different strategy, namely a fabrics-based tactile sensor, which is only a few millimeters thick. So we could cover also the palm and all the phalanges, which gives us pretty good coverage now of all the palmar side of the shadow hands with some sensing. So how do these sensors work? All what we do so far is piezoresistive sensing. So we measure the change of resistance between two electrodes due to applying pressure, and this has two major contributions. One is we increase the contact surface when pressing the sensor onto the electrodes, which is, I would say, the major effect here. And then we have some internal change of resistance due to the piezoresistive effect in the sensitive material. So, of course, we want to have also very sensitive sensors reacting to very small forces. That's why we studied how can we increase the sensitivity, and it essentially boils down to the structure of the electrodes. So we tried different electrode shapes, and it turned out that that maximizing the gap between the two electrodes gives us the highest sensitivity. So we use the M-shaped central layout now for all our sensors, which gives us best performance. And yes, of course, we have hysteresis effects, as Matteo already mentioned before. So we have a different loading and unloading curve. But my argument is that we don't really care about the absolute forces when dealing with manipulation. All that matters is relative forces. And yeah, we have also a strong nonlinear effect here, which is from an engineering point maybe not very nice to have, but actually it helps us very much, because we have high sensitivity in the very beginning of the range and low sensitivity in high force ranges where we don't care much about the force. Matteo was several times already mentioned the spatial super resolution, which we also have here. So if we average over all the tactile positions in a tactile block, so that's a typical tactile block you observe if you press this tactile array, then you get much better resolution than the actual sensor size. So the sensors here in the individual tactiles have a size of 5 by 5 millimeters. However, if you move now such a probe tip across a single sensor and you estimate the contact position by averaging over all these contact locations, then you can nicely follow the position. So this whole distance is here for these 5 millimeters. However, we always stay in the range of a millimeter about the actual position. So we increase by a factor of 5 at least, which comes already quite close to human resolution as well. So as I said, we also want to record human interaction episodes, so we need to measure interaction forces when humans deal with objects. And our first idea was to simply sensorize objects with our tactile sensors. And the very simplest idea was to create a kind of tactile book, simply taking 4 of these flat sensors together to have a book-shaped object where we have now a lot of these tactile sensors available. And we did some basic experiments here, humans grasping these books, and then created some perturbation using these phantom devices here, and we can measure them, the tactile interaction forces or grasping forces of the individual digits. And what was found then that humans, of course, quickly react or quickly adapt to those perturbations So in the very first perturbation, there was still a high post-deviation error, but more subsequent perturbations, this error decreases quite fast, and the grip force here increases accordingly. So you stiffen your grasp in a kind of synergistic fashion. All our fingers are tightened together so that you can more stably hold the object. So another object we built then was the tactile cam, which is simply composed of 10 of those strips, tactile strips. And we have also a motion sensor integrated so that we can track the object over time. And we have different options for the top, so we can have a vision marker or a simple gripper to hold different objects. So the humans can actually use this kind of object as a handle and doing some tasks. However, all these objects, not all of our objects we can really sensorize, so we thought further and essentially came then after the fabrics-based tactile sensor, which we already also used finally then in the shadow hands. And this fabrics-based sensor gives us high flexibility. We can cover all kinds of 3D surfaces, and using some clever etching techniques, we can also produce several pixels here, so we can measure normal forces in different regions of the hand. And the very first study we did along that line using this graph was a haptic search study. So humans were asked, blindfolded humans were asked to memorize a kind of tactile pattern and to find that pattern in a larger area with a lot of distractors in it. And what we observed was a lot of different exploratory procedures. First of all, having kind of global search strategy where we used a flat hand, kind of localizing ourselves in this local pattern, and then some local verification strategies using fingertips only, surface and edge following strategies, and so on. So to manage this large zoo of tactile sensors, we also proposed a tactile toolbox for ROS to acquire the data and manage the data over time. So what we proposed is a set of messages in order to publish the data and also to process. So we have on the one hand the raw measurements, which are published here by some driver and publishing as a tactile state, and then we have a simple merger component which can aggregate the raw signals together with some position information which is stored in the UDF file, providing the position, the normal, and the shape of the tactile sensors, so that you can, on the one hand, visualize them, and on the other hand, compute the contact position from that, and also the force direction. This is then also augmented by some gazebo plugins, which we use to simulate tactile data. So gazebo gives you quite accurate position information, exact to the point, but our sensors typically, as you have seen before in this tactile image, kind of blur the exact contact position. So in order to mimic that, you need some other gazebo plugins. And we also use these sensors to robustify our autonomous grasping scenario. So what you see here is that we can segment that scene and choose a grasp based on this segmented object shapes. We essentially fit some basic geometric shapes and then choose the grasp for them. And using now tactile feedback, we can, for example, notice when in such a hand-over task, when the human essentially takes the object, so we apply some forces by taking, which can be noticed by the sensors. We also notice now that we lost the object, so unfortunately there's no sound. Which was always difficult before when we didn't have tactile sensing. So we grasped an object, and even if we lost it, we proceed with our task all the way down to the end, which was always kind of funny for the visitors to see. But now we can have this. Stop. Okay, so we notice that we lost the object, and we also notice if there's some object in the way if we don't yet expect some context here, and we don't anymore crush into the objects. Another important question to solve for grasping is, of course, how much force to apply. And what humans do is to use slippage information in order to increase grasping forces as soon as slippage occurs. And this slippage generates essentially micro vibrations in the range of 400 Hertz, which are amplified by the fingerprints. That's why we have fingerprints in our human hands, and biotech has fingerprints as well. And those micro vibrations are quite fast, 400 Hertz, and that's why we wanted to have very fast sensors in the very beginning. But using now our sensors, we can indeed train a neural network to detect this slippage and increase the grasping force. So you see here that we hold this very fragile plastic cups, filling in more weight. The object kind of starts to slip, although you don't see that visually. These Mickey Mouses here turning red indicates that there is slippage detected by the neural network, and you see that the fingertips close further in order to stay with the object. So that works quite stable. And looking at the data sets, you see, well, it seems to be a rather simple task. The TSNE embedding of this data is quite separated already, which indicates that you can easily distinguish these two data sets. So what about more complex, more difficult slip detection tasks? On the one hand, we could try to distinguish different types of slip. So static situation, of course, then translational slip, versus rotational slip. If we are looking at this kind of data, it looks already much more complicated in the TSP embedding. And if we go from the flat sensor, which is very rich in information, we have 16 by 16 pixels, now down to the fingertip sensors, where due to the curved shape, we have typically only 4 by 2 by 2 pixels activated at a time. This becomes a little bit more complicated to classify. And another important task, I don't know who mentioned that, taking out the book from the shelf, we slide an object across some surface. However, nevertheless, we need to distinguish whether we actually slide the object or we slip over the object. So here we tried that on the horizontal surface, trying to push objects on the table. and distinguish whether we actually push the object or we slip over the object. And again, the data set looks not very promising. So we need better methods, and our way to go was to speed convolutional networks. Essentially, because we try to classify vibrations, it makes sense to pre-process the data into Fourier spectrum. So for each texel, we essentially have a Fourier spectrum over a time window, which gives us here 32. Let's phrase some power images. So 32 image channels. The grid-like structure of the tactile array can, of course, be used so we should use this grid-like structure of the data for processing. That's why we use convolutional networks, which kind of preserves the structure, and then we can solve these tasks quite successfully. So you see that we can apply that slip detection now also on the shadow fingertips, and even also for this sliding with versus sliding on task, we achieve quite high accuracy so that we can distinguish these two situations. So finally, let's come to tactile servering. How can we use the tactile information directly in order to control the robot end effector? And the idea is rather simple. We have some tactile features, contact position, for example, the contact force. Maybe if we have an elongated contact block, we can also extract the orientation of the object edge on the sensor. And we want to map, or we want to directly control them. And the basic idea is to directly map errors in those features onto appropriate motions of the sensor. So for example, if you have force errors, you simply move along the normal direction. If you have position errors, you can translate your sensor in the plane perpendicular to the normal. Or you can also roll about the object, as you have seen here. And of course, you can then rotate around the normal in order to orient the object edge. And if we take everything together and add some external motion components in a kind of open loop fashion, then we can follow arbitrary line segments, for example, or we can explore an unknown object surface, as you see here. And doing that with two hands now, and collecting all the data, all the tactile data into a single frame, which is here done by vision. We can collect a tactile point cloud and get a rough object shape from tactile sensing. And that works not only for smooth surfaces, but also for edges. So let's have a look at this kind of controller. As I said, we kind of measure its features and compute an error. And then we simply map these errors onto Cartesian motion of our end effector, which is the translation along the normal, or the translation in the plane here, or this rolling motion. Then we can choose with a projection matrix which components are relevant for a task, transform all that into the world frame, use inverse kinematics to compute joint velocities, integrate for position controlled robot, and then we have closed the low-level tactile serving loop. And then we can feed in higher-level signals in order to explore surfaces, for example. And for that, we use here, for example, a vision loop. which adds this kind of feed-forward motion in order to explore the object. And we can use that not only for exploring the surface, but using different cost functions. We can try to optimize the grasp, contact location before grasping, and we can also use these strategies in order to move the object around. So always using these very simple tactile solving strategies under the hood. So there's no knowledge about the object here. It's all reactively driven. So, and that's at the end. That's thanks to all my collaborators who did all this interesting work, and I'm open to questions.
The vibration sensing for incident slips interesting. Do you see vibrations from the robot drivetrain at the same frequency?
We see those vibrations as well, but they are in a different range, and that's why the network can try to distinguish that. But it's indeed important to acquire training samples with the robot moving. So we essentially slip with the robot over some surfaces in order to have that involved during training as well.
So I hope as for the slip detection, so is your method that can be generalized, for example, for different shapes of objects or objects with different kind of surfaces?
So far, we didn't use or employ the method for specific subset of materials. So far, it seems to work for all kinds of materials. So typical materials we use in our lab setting. So we didn't study that in very depth yet.
So are the signals different according to the materials?
The signals are kind of different between various materials. So there are other approaches where you can try to classify the material based on the kind of signal. But for slip detection, it seems to suffice that you have kind of typical vibrations in the signal that you can notice. Okay, there's slip.
So, well, let's thank our speaker again.